Hello there. My name is Christopher Reither. I'm from Copenhagen University, and we've been doing some work on the within-network classification problem, which, in short, is just basically accurately classifying nodes within a network. We present results using two approaches. One is extracting label-independent features from the graph. Another one is using these latent linkages that exist in graphs as well. In the later approach, we modify these graphs by adding edges depending on these attribute informations that are inherent in the data sets. And then we use off-the-shelf label propagation algorithms to see if we can boost this performance. We compare performance on some real-world data sets and show that by using these methods, you can yield better results than off-the-shelf classification algorithms. Thank you.
Hello everyone, my name's Ben Chamberlain. I'm from Imperial College London and ASOS.com. And I've been doing real-time community detection in large social networks on a single laptop. So what we do here, actually the large social network in question is pretty much all of Twitter. And so that's 700 million vertices and 20 billion edges. And so what we do is we take a group of vertices from Twitter. In this example, I've taken Diageo and some of their sub-brands. We run a local community detection algorithm where we define similarities between vertices to get a candidate set of vertices. And then we structure that in some way using a global community detection method. So for Diageo, what comes out is, unsurprisingly, loads of different types of alcohol. So to get this onto a laptop, we define similarity between vertices using the Jacka coefficient of their neighborhood graphs. And then we can compress that using min-hash signatures. And then to get a sub-second query time, what we do is we band up the min-hash signatures and build a locality-sensitive hashing data structure. So we can query the whole thing in under a second. It fits on a laptop just like that one there. Thanks very much. That's what I got.
So hello everyone, my name is Shuangfei Fan. I'm from Virginia Tech, and the name of our paper is Training Iterative Collective Classifiers with Backpropagation. The co-author is Bert Huang, my advisor. So we just proposed a differentiable variant of ICA, which allows better loss optimization. It corrects the discrepancy of the between the learning and the prediction algorithms in ICA with incorporating principles using deep learning and the recurrent neural network into the training procedure. So the results showed in Figure 1 prove that by training with BPICA, we more directly optimize the training loss of collective classification, and which translates to improve the accuracy and the robustness on real network data, which is the results showed in Figure 2. So this settings is more challenge. So this settings is more challenge for ICA when the local classification is very noisy. Okay, thank you.
Hi everyone, I'm Hongxia Yang from Yahoo. So we are currently working on the Bright-Roll demand-side platform. And every day we receive like billions of bid requests from the users. And we serve like thousands of different campaigns. So this work is motivated from this real application. So basically speaking, this is a highly lopsided bipartite graph. So first we design a novel bipartite graph to include these different edges and weights. Second, we design an efficient adaptive Nebo algorithm with two sparse version extensions. Third, in this work, we also show a very good amount of ROI, return on investment improvement in the reality. Thank you.
Good morning, everyone. My name is Yibo Yao. I graduated from Washington State University, and my advisor is Dr. Larry Holder. Our paper is about detecting concept drift in classification over streaming graphs. So the streaming graphs we also refer to as a graph stream, which is an endless sequence of graphs, and as they are received sequentially over time, and they are independent from each other. Each of them has associated class label. So the classification over streaming graphs is to design a classification technique for those graph streams, and our paper is about detecting concept drift, and we developed a concept drift detector for the classification process over stream graphs. So what we did is that we maintain a fixed size sliding window, and inside that window, we compute the graph entropy for all the graphs inside that window. And when we move this window forward, then we will have another graph entropy. And when the graphs keep streaming in, and when the sliding window move forward, we will have a series of entropy values. So we use some technique called cumulative summation to check if there is a significant deviation on the graph entropy series. If there is, then we are able to tell where the concept drift is likely to happen. And more details are included in our poster. Thank you.
Hello, this is our work on local spectral diffusion for robust community detection, and I'm Kun He from Huazhong University of Science and Technology. This work is with my student Pan Shi and 2 faculty at Cornell. So we designed a new method for finding local communities in large networks from very few seed members. In our work, we define a series of local spectral subspace based on Krylov subspaces using different probability diffusion methods and find a relaxed indicator vector on the Krylov subspace to extract a community. We thoroughly test on both synthetic and real networks. Our method outperforms state-of-the-art algorithm, heat kernel, PageRank diffusion, and previous local spectral methods. See the 2 figures. The left column are our result, and in the first figure, and the other 2 are heat kernel and PageRank. And the right figure, the first column are our result, and the 2 others are the 2 previous local spectral methods. And see details in our poster. Thank you.
Good morning, everyone. My name is Giselle Seno. I'm from Purdue University, and this is joint work with my advisor, Jennifer Neville. If you're familiar with collective classification, you might know that it's been shown to perform really well on a variety of different real-world networks. The goal of our work is to generalize from these empirical results. To do that, we've been using synthetic data so that we can control the network characteristics, various network characteristics at the same time. In particular, we use a generative network model to do this, and we vary the attribute correlation and the link density. So in these plots that you can observe, the points that you see are actually networks that we generated, and the y-axis is their respective correlation, x-axis the density. The surrounding color represents the AUC scores obtained with collective classification. One finding that we have is that when the link density is low, we actually higher attribute correlation to have better performance. But conversely, we've also found that with higher link density, we can achieve similar results even with lower attribute correlation. If you come to my poster session, I will have more results to show. So if you come talk to me, I can talk more in detail. Thank you very much.
Hello, everyone. My name is Sal Aguinaga. I'm from University of Notre Dame. When we study complex networks such as communication networks or networks that we derive from of the brain, we derive graphical representations to work with. Oftentimes, during the validation of a new method, we are interested in similar networks. In other words, networks that exhibit similar network properties. To address this, we can pick one of several well-studied network generators to learn a model given a graph. For example, Kronecker product, Changlu BTR is one of several. Using the learned model parameters, we can generate synthetic graphs, which on the surface have many of the similar properties that are found in the original graph. But how do these models capture the intricacies and interactions to be able to scale? Or how do we shed light on the biases and assumptions that are made at the core of these models? One way to do this is using a simple method we call infinity mirror, which takes a newly created synthetic graph, we feed it back to the generator, we learn a new set of parameters, and then we compute some network properties and compare those against the original network. At each step, a new synthetic graph is generated. We compute a battery of network properties, and again, we compare those to the signature of the original graph. This way, we can see what network properties are consistently preserved and which ones are not. And if you come to my poster, I can go more into detail into that. Thanks.
Hi, my name is Piggy, and together with Alisa Getur from UC Santa Cruz, Chris Markham and Laura Colley from NIH, we worked on entity resolution in familial networks. So the problem we are trying to solve is to reconstruct an underlying familial network given a set of partial egocentric views of this network. Partial egocentric means that the network is described from the point of view of a single person. Because of this, data and relationships that are given to us may be inaccurate, missing, and incomplete. Here we see a motivating example where we have two partial egocentric view. The one is from the point of view of Annabel Perez and the other one from Jose Perez. And our task is to identify that persons in same colors represent the same entities. White boxes do not match across trees. In our approach, we first infer missing relations. For example, a mother relation may indicate a child relation. Second, we generate features by computing similarities based on both personal and relational information. Third, we use a classification-based approach in order to define if a pair of persons represents the same entity. And finally, we address the one-to-one matching restrictions problem. So if you want to find out how effective our solution is, please come by our poster. Thank you.
Hello, my name is Joseph Crawford, and I'm from the University of Notre Dame. So let's say we have two different networks, one where we know a lot about one network, but not so much about the other. What we want to know is there a way to take knowledge we have on the well-known network and apply it to the network we don't know too much about? Well, this is one of the problems we address in network alignment. Network alignment aims to find regions of similarity between two different networks and has application in domains such as social networks and computer vision. Now, there are two different types of network alignment methods. One being local network alignment, which aims to align networks optimally, which results into small conserved network regions, and also results in high functional quality but low topological quality. And then there's global network alignment, GNA, which aims to align networks suboptimally, resulting in large conserved networks and scores high topologically but poor functionally. So what we want to know is there a better way to perform network alignment? And in our study, we present our method IGLOO, which takes components from both LNA and GNA. And if you see in our figure, with respect to LNA methods, we're able to have superior scores both functionally and topologically.